right, we are going to take a look at continuing problem number 23, which discusses a curve that is banked for design speed of 23.6 meters per second and has a radius of 78 meters. We discover that that creates a banking angle of 36 degrees. And today what we want to look at is how slowly a car could go and still maintain the height on the bank. Well, in order for a car to stay in this position and not slide downhill, we need something else to add into the centripetal force holding it on the hill. If it's tending to slip downhill, then the force has to be a friction force pointing up the hill. And that friction force will have components that point along our artificial X and Y axes. So I'm going to draw those components in yellow here, projecting over to this axis. That's FF in the Y direction. And here we have FF in the X direction. So what this does for us is this is going to generate another set of equations, but let's get it set up thinking about those components of friction and how they affect the normal force as well. So we know we have FF in the X direction. If you follow theta around, you'll then notice that that component can be calculated by multiplying the friction force times the cosine of theta. FF in the Y direction, that's the vertical component, is going to be FF times the sine of theta. And then remember, there's two other things that we can look at here. First is that the friction force overall we know to be mu, and in this case static mu, times the normal force overall. And then if you look at what's going on along the y-axis there, you'll realize that the weight, which is mg, has to be equal to the friction force in the y direction, that's the yellow vector, plus, and I did not draw this, the normal force component in the y direction. All right, what we're going to do is combine this information with stuff we already know, and that is what we know about the centripetal force. And we know the centripetal force is equal to the net force pointing toward the center of the circle. And the center of the circle in this case is where I have drawn that toward track center. So FC is equal to Fn in the X direction minus the friction force. We did this qualitatively the other day, but really didn't fill in much else. So that's mv squared over r. And of course, if we break up the normal force into its components, we see that they're related to the sine and cosine of theta as well. And there's FF cos theta. All right, from here, what's interesting is, of course, this becomes mu s times Fn cos theta. And with a little algebraic trickery, all right, I'm going to factor out an Fn on both of those terms. Now, you may say that that's really not fair, but it is interesting because if I then go like this, what I've done is I've created a situation where I know all the values in this particular problem for everything in here. So like I know theta and I know mu and I know theta again and I know r. So I don't know what the mass is, and I'm trying to find out what is my minimum speed, how slowly can the car go, and I don't know what Fn is, but never fear, okay, because I also have something else I can draw on. Also, I know this, okay, and that on the left side is really mg, and ffy, I know from right above there is f times sine of theta plus fny, and that fny term is just fn cos theta, and yippee, I have worked in f normal again because of this fn sine theta, and guess what I'm going to do? I am going to factor out that fn again. mg equals fn times mu s, sorry, that's one term, yikes, that looks terrible, mu s sine